Hey everyone! In this video, we're going to look at how a sub-GHz decoder and encoder are implemented in the Flipper Zero. I will describe all of the methods and then we'll walk through an example decoding a came 12-bit signal. The approach is the same for both static and rolling codes, although rolling codes usually has more complex logic. Using this technique, you can analyze the various protocols supported by the Flipper Zero and hopefully troubleshoot when a signal is not getting decoded. Let's get started. There are 8 key methods that make up the decoder. Alloc allocates the resources needed by the decoder and it loads any configuration data. Typically, this method's invoked when SubGHz application starts. Free frees those allocated resources and it's typically invoked when the application exits. Feed gets invoked and it gets past the level, which is on or off, and the duration of that pulse, and it processes those pulses. And once it detects a sequence of pulses that makes up the full data, it sets that generic data count bit and data. Reset resets the feed to that initial state. Deserialize processes a subfile and then it sets the data count bit and the data. For example, here it would set the count bit to 12 and the data to 0x5461. Get hash data returns a unique value based on the data count bit and the data. And this unique value is used to compare with the previous signal to see if it's a new value to add to the history or if it's already in the history. Serialize takes that data count bit and data and creates a .sub file. The subfile also includes frequency, preset information, and protocol information. Finally, getString returns the text that's displayed on the Flipper screen and also in the CLI, which is the command line interface. There are 5 key methods for an encoder. Alloc allocates the resources needed by the encoder and loads any configuration data, and it's typically invoked when the application starts. Free frees the resources, and it's typically invoked when the application ends. Deserialize is similar to the decoders deserialize, and that it processes the .sub file and then it sets the data count bit and the data. But then it also sets the upload array, which is an array of level durations containing both the duration and the level. And then it sets size upload, which is how many values are in that upload array. And then it sets repeat, which is how many times it's going to send the signal. So a repeat of 1 means it'll send the signal once. And finally, it sets the encoder state to running. So as the sub-GHz is trying to transmit a signal, it will call yield, and yield will check to see that the encoder is running and that the repeat is at least 1. If it's not 1 or it's not running, it will return a reset level. Otherwise, it returns the next level duration and then it increments the front pointer. And so now the front pointer is at the next spot. And it checks to see if that's the end of the list. So if it's equal to the size upload. And if it is, then it decrements that repeat counter as well. So this is just a tight little loop in yield that returns the next level duration, which is that duration and level information. And finally, stop in almost every encoder I've looked at just sets the running state to false. Now you know how the Flipper Zero decodes and encodes a sub-GHz signal. Please like and subscribe. And for the remainder of this video, we'll be debugging an actual raw signal, looking at that decoding. Feel free to jump to the end of the video if you don't currently need to debug a signal. I've opened Visual Studio Code with the official firmware, and under lib, sub-GHz protocols, you'll find all the different decoders and encoders. So we'll go ahead and open the came.c file, and I'll go ahead and pin that. So typically what you'll see is some pound defines here that define how many bits are in the protocol. And then you'll also see this part here, which is very helpful. The TE short is how long a short pulse is. The TE long is sometimes not used, sometimes it is used. And the delta is how much plus or minus the short is typically how that's represented. and then how many minimum bits are needed for the signal. Then there's usually some kind of structure here that you'll see that has the base and the decoder. And then next we have the sub-GHz protocol decoder with those 8 method values. And then this points to those different methods. For example, if we click on alloc and go to definition, you can see this is the alloc method. After alloc, we had free, we had our reset and our feed. You can see our feed takes the level, which is a true or false, and the duration. And then our get hash data that calculates that unique number. There may be some collisions since it's only an 8-bit number, but it helps basically figure out if the history should be updated or not. And then we have that serialize that was creating a .sub file, and deserialize that was taking a .sub file, and then get string, which is determining the text to show on the flipper and in the CLI. So next I've opened in assets unit test sub-GHz, the came_raw.sub file. So we'll go ahead and right click and reveal in File Explorer. And then we'll open QFlipper. And in QFlipper we'll go to SD card sub-GHz. We'll drag our came.raw file over. And then we'll close QFlipper. Next I'll open the CLI and we'll do sub-GHz help, and then we'll do sub-GHz decode raw ext sub-GHz came.raw.sub. Good. And so we can see that there's a bunch of packets that are came 12-bit. Okay, so let's go ahead and launch our debugger and continue. And then in came, we'll set a breakpoint on the step reset, and we'll set a breakpoint inside when we actually have found something that meets our requirements. And then we'll rerun the decode raw. Again, that raw signal is 1601 and then negative 32.7 and 381. And so we're here. Our level is true, which means it's a positive value. There's signal. And our duration is 1601. Since it's not true, then this code's not going to run. And this time our level is false. It's a negative. And so not false is true. And our duration is 32,700. Our short is 320. And our delta is 150. And so our short is 320, and we're multiplying that by 56 here. So that's 17,920. And then we're doing a diff of that and our duration, which was 32,700. And we're trying to see if that difference is our TE delta, which is 150 times 47, which is 7050, which means that our value of 17,920 plus or minus 7050 is 10871 to 24970. And so 3200 is not. This time our duration is 381 positive, so that's here. Okay, we're here. I'm trying to get us over to here. Okay, our duration is 23,000, and 23,000 is in that range of 10,000 to 24,000. Okay, so we're about to start and transition into our start bit. I'll go ahead and set breakpoints each of these stages. And I'll clear the breakpoint from here. And I'll set one here. Perfect. We can see the level is true. And our duration is 351. So we're right here right now. And 351, our TE short is 320. And our delta is 150, so that is within range. So our next step is going to be save duration. And we're clearing our data and our count bits. Now we're in save duration with the next signal, which is false, and not false is true. And this time our duration is 324, which is not greater than 320 times 4. And so we're setting our TE last to 324. And our next step is going to be check duration. So now we're in check duration. Our level is true. Our last is 324, which compared to 320 plus or minus 150. And our current duration is 677 compared with 640 plus or minus 150. So that looks good. So we're going to go ahead and add a 0 as one of the new bits to our code. I can go ahead and step into that, I guess, this time around. And you'll see it takes the existing data, shifts it 1 to the left, and then ORs the bit, which is either a 0 or a 1. It's a 0 in this case. And then it increments our bit count, which is currently at 0. So our data is now 0, shifted over, and then ORed with 0, and our bit count was 0, and now it's going to be 1. And their next step is save duration. So that's the first bit we've processed so far. Our level is false. Our duration is 322, which is not greater than 320 times 4. So we're going to go ahead and save that duration of 322. And this time, our level is true. Our last is 322. Our current is 655 compared with 640. So we're going to add another 0. I'll go ahead and step over it this time. There's our level is false. Our duration is 654, which is a bigger value this time around. But it's still not 320 times 4. So we're going to save our last duration, which this time is 654, and set our next step. So this time, our level is true. Our last is 654, which compared to 320 plus or minus 150 is not correct. And so now we're going to compare 654 with 640 plus or minus 150, which it is. Our current duration is 335, which compared to 320 plus or minus 150. So this time we're going to add a 1-bit. So I'll go ahead and step into that. So our current data was 0. We went ahead and shifted it over to 0 shifted by 1 is still 0. And we ORed it with that bit of 1. And so now our data is 1. Our count was 2. It'll now be 3. Okay, and that's false. Our duration is 352, which is not 320 times 4. So we'll go ahead and save that 352. Our level is true. 352 compared with 320 plus or minus 150. And our current duration is 661, which compared with 640 plus or minus 150 is correct. So we're going to go ahead and add a 0. And this time I'm going to step into that again. Our old data was a 1. We're going to shift that 1 over 1 bit. And then we'll OR our 0. So this time our data is now a 2. And our count bits was 3. We're going to add 1, so we'll be at 4. And this process will continue. We'll go ahead and look at this point. Our level is true. Our last was 672. So our last was 672 compared with 640. And our current is 343 compared with 320. So we're going to go ahead and add a 1 bit. I'll step into that. Our current data was 133. So we shifted that 133 over, and then we ORed a 1. So we have 267 decimal. And our current count bit is at 10. It's now going to be 11. Our last is 314. Compared to 320, and our duration 661 compared to 640. So we're going to go ahead and add that 0 bit. I'll step into that one. Our data was 267. We're going to shift it. And then we ORed with a 0 bit. So that puts us at 534. And our count was 11, and we're going to add 1, so we'll be at 12 bits. We have a false there. Our duration is 22996, which is much bigger than 320 times 4. So we're setting our next step to be start bit. And then we're checking our count bit, which is 12, and seeing if it equals the minimum count bit, which is also 12, so it does, or if it equaled the Air Force count, or this count, or this count. Any of those exact values would follow us into this thing where we're going to go ahead and clear our serial, clear our button, and then our data of 534, we're going to set that, and our count bit of 12 we're going to set. I'm going to go ahead and clear this to give us an extra breakpoint that we can handle. And I'm going to set a breakpoint in getString, because I have a feeling that this callback is going to end up calling our toString to output display data. And it looks like it is. So if we switch back to the CLI real quickly, you can see we currently have not printed anything here. We're just listening. So our generic data is 534 decimal, and we're going to end it with 4 billion, which is going to have the effect of dropping any high bits to 0 and keeping all the low bits as they are. Next, we're going to set code found reverse. Based on this, we're going to pass in that data, 534 decimal, and our bits of 12 bits that we want to reverse. Let's go ahead and step into that. So we set our reverse key to 0, and we're going to keep incrementing that. We're going to take our reverse key and shift it and OR in the bit that we read. So it's going to have the effect of starting with 0 and then shifting each of the 12 bits over. So let's go ahead and step through that. And so you can see reverse key is working. So we'll step out of that. Okay. At this point, we have our reverse set, and we have our code found reverse low is code found reverse, masked with a bunch of zeros and then the FFFFF. So this is going to be the lower 32 bits of that reversed value, which is 1668 decimal. And now for our output, we're printing the name of the protocol, which we're going to look and see the data count bit, which is 12. If it equals this many, which it does not, we would print that value. Otherwise, we're going to see if it equals, the count bit equals this exact value here, which it does not. So otherwise, it's going to print out the protocol name, which is came. Second value, %d, is our data count bit. So it's going to say 12-bit. And then our key is going to be 0x and then 0 filled, 8 digits, a long value, hexadecimal capitals. So we'll take that 534 and convert it to hex as caps. And then our yuck is 0x, 0 filled, 8 digits, long value, capital hexadecimal. And so we will take 1668 and convert that. So let's go ahead and pull up the calculator. And again, 534 decimal is 216. 1668 decimal, 684. Okay, it's now processing the next signal. But here we can see that it got the 216. And the 684. Hopefully now you know the 8 methods used for decoding a sub-GHz protocol and understand how you can use a debugger to debug a raw capture to see why a signal is or isn't getting detected. Please like and subscribe, and if you have any questions, please leave a comment below or on my Discord server.